You can do more with UV light. I'm going to talk about that. This so far was all about disinfection, but you can also oxidize with UV light. And this is important because disinfection is an application, everybody knows it, but now in Europe we're looking more and more at other things in our water. A reason for that partly is that our water became cleaner and cleaner the last 30 years. Things like phosphate and nitrate are largely taken out of critical surface waters. So what we see on one hand from a chemical perspective, water has become of higher quality, but we still see struggles in biodiversity, ecotoxicity. Species we were expecting to come back in our ecosystems are not coming back, are still struggling, and we think one of the reasons this happens is there are a lot of anthropogenic compounds in the water. So compounds from us, we use in our life to make our life easier or healthier, but that have very subtle effects on other things in the water. And these can be medicines, hormones, cosmetics, pesticides, antibiotics, of course, drug waste. In the Netherlands, it's in some areas quite a big problem. Contrast agents, preservatives, additives. These last two are a funny one because preservatives are in our food and most of those are not as bad. But for instance, in cosmetics, quite a lot of antibiotic-like substances are used. For instance, the cream you have in the bathroom, it's technically, chemically, a pot of fat. Bacteria like it. You keep it in a warm, wet room, you put it on your face every day and nothing grows in there, which is weird because every other type of waste we know, at some point it starts rotting. So in that pot of cream there are a lot of compounds that prevent biology growing in there. So a lot of the things we use, the clothing we wear, has these compounds that have some ecotoxic or biologic effect. Antibiotic resistance, one of the biggest health problems we expect in the future. The WHO is warning about it more and more. And we expect an era in the future where simple infections can start killing again. For us as young people, or you as young people, we've never had a time where infections killed us. 200 years ago, it was normal to get a wound and to die from it just because you had a little wound. And the reason why we have such good development the last 150 years, to a large degree, is dependent on the antibiotics we have and the health benefits these have provided. And there might be a time when that stops. Fertility. Western males are getting less and less and less fertile, to the degree when we expect in 2040 that only 20% of Western males can still impregnate their wife without the help of medical assistance. Which is weird because as humans, as organisms, procreation is almost our most fundamental thing. So if societies get less fertile, there's really something happening. But also diseases like Parkinson is linked to pesticide use more and more. In France, Parkinson is deemed a professional disease for farmers. Also in the Netherlands, there's a lot of discussion about Parkinson and what causes it. It's starting to become quite clear that pesticides have a large influence on this. Pesticides farmers breathe in when they use them, but also pesticides we get in our body when we eat food or food that is grown from surface water that contains it. And this is a bit of a controversial slide. Some people don't like this aspect, but in a way you can expect medicines and pesticides to almost be developed to be persistent. Because if you use a pesticide or a medicine, you want a compound that's really active in small amounts, so you don't have to use a lot. It stays in your body longer, it works better, and you want a compound that isn't degraded easily, so you have to dose less and less often to have the same effect. And it's not biodegradable, etc., etc., so you have a long shelf life. And for these medicines and pesticides and additives, this is a good thing. But for the environment, this can also be a bad thing, because it means you're making compounds that are very active and stay in the environment for a longer time than other compounds maybe. I'm not saying we shouldn't use these, but it is more and more important, especially in Europe, to take these compounds out of the water again. And that's what we're doing about it as a technology provider. And what can we do about it with UV light? Back to UV. Two things. Direct photolysis, quite a lot of compounds absorb UV light. For instance, diclofenac can be broken down quite easily just by illuminating it with UV light. Even a disinfection system with a reasonably low dose can already reach quite significant degrees of diclofenac reduction. But for many compounds it's not enough. So you can do more with UV light, and that's a technology we're actively developing. You can also add hydrogen peroxide to the water. Hydrogen peroxide cleaves into hydroxyl radicals when you eliminate it with UV light. And these hydroxyl radicals are the strongest radicals, or the strongest oxidizers we know, apart from fluorine. As you can see here, fluorine is the strongest oxidizer. The hydroxyl radical is below it. We don't use fluorine because it's an extremely aggressive gas that nobody in their right mind would just pump in the water. So the next best thing, this hydroxyl radical, we make it in situ by illuminating the hydrogen peroxide with the UV light. We only generate the radicals where we need them, and these radicals oxidize the pesticides, the medicines, the hormones in the water directly, turning them essentially in their mineralized end components like CO2 or biodegradable pieces of that. Here you can see the difference between the two. This is a number of compounds. It's spiked in drinking water. It's treated with 4,000 joules, so quite a high UV dose, and a little bit of hydrogen peroxide. And you see some bars that are entirely yellow. That means all the deterioration is from direct photolysis. You see some bars that are almost entirely red. This is the oxidation part of the hydroxyl radicals. And you see some that have both. And you see some compounds that are really difficult to remove on this side, and some compounds that are really easy to remove on this side. And this is what we do quite a lot in projects for surface water, for drinking water. The European Union now defined a number of guide compounds you can measure, and they have checked that they correlate well with other compounds, but they're also important to take out of the water. There are standards for that, and there's also regulation now where we have said in the European Union we want to remove these compounds actively from the water. And that's what we use our advanced UVC system for, Advanced Oxidation system. We've made a specialized reactor. We add a little bit of hydrogen peroxide. The hydroxyl radicals burn the compounds in the water. And in the end, you have removed these compounds permanently. You've oxidized them. And because of the UVC dose, smart people here would have seen the 4,000 joule. For drinking water disinfection, you used 400 joule. So the fun thing is you get disinfection for free. And that is important, especially when you're talking about antibiotic resistance. You don't want to just remove the antibiotics, but also the resistant organisms, the actual causative factor, but also the free genes that can transfer these antibiotic resistant traits to other bacteria. So it's not just a solution for the compounds, but for the whole matrix. And we feel that's very important to solve as much problems as you can. But of course there are side effects. What happens to these compounds? You're oxidizing them. Maybe you're producing new chemical species that might be more toxic than the ones you originally had. If you have 20 complex organic compounds, the number of oxidation products is an order bigger. And for most of those products, you don't have toxicologic data. There's nobody who measures every single compound and every single permutation of that. So generally, you don't have enough toxicological data to really say, watch for this one should be this low, or etc. So that's why in the Netherlands we use effect tests and bioassays a lot, where you're not looking at individual compounds, but you're looking at assays that can measure ecotoxicological, genotoxicological, or biological effects in the water, and can say if the water gets more healthy or less ecotoxic. There are a number of ones that you can use. The Simony score is currently a method that combines a number of these into a score, which is nice. That works quite easily. And what you see here, the red bars, are the water as it coming currently out of a sewage water treatment plant in the Netherlands. And we want to make it better. So we have applied ozonation and we have applied UV in a project with a competitor that gave another technology. And what you see is you always have an increase in water health. So your Simony score gets lower, which means the water is more healthy, more environmentally friendly. And what you also see, the more compounds you remove, which is the percentage above, the less or the more that healthy effect becomes. So it shows two things at the same time. The amount of compounds you remove, but also a positive water health effect. There are other things also used. Algae are used a lot as a sort of a bioassay. Crustaceans that are very sensitive to these compounds. And there are standardized tests, for instance, microtox, that use special bacteria. In these cases, you can only prove a low to negligible effect, just the way the test works. Another important thing is, are you not forming, for instance, bromate, which is an oxidized form of bromine in the water that can be carcinogenic. So that's an actual physical parameter you also measure.